Well, good evening. Welcome to another instalment of me fumbling my way through a critical care skill. Tonight we'll be going through arterial lines, waveform, interpretation and safe transport. Now, invasive blood pressure monitoring through a arterial line is it's indicated to monitor deterioration of a patient with cardiac instability, can be used as a diagnostic tool to determine causes of physiological shock, like pulsus paradoxus, evaluation of fluid resuscitation responsiveness. You might consider an arterial line in monitoring a patient with morbid obesity who can't fit the blood pressure cuff adequately. And it's really useful when we want to closely maintain a target mean arterial pressure while administering vasoactive substances, vasopressors or dilators or something like that. Now, invasive blood pressure monitoring is a real-time invasive monitoring. It's good to monitor cardiovascular insufficiency, constantly measures the mean arterial pressure and pulse pressure. Now, the things we're going to need for this, which I don't have here because unfortunately I don't have any equipment, we're going to need a patient, of course, and a functioning arterial line. We're going to have a monitor that's capable of showing a arterial waveform. We're going to have a 500 ml bag of normal saline, which is going to be inside a pressure bag inflated to 300 millimeters of mercury. This is going to be set up to be a slow infusion of 1 to 3 mils per hour. We're going to have a pressure transducer, a line that's about 48 inches long, primed, has to be non-compressible, pretty much a rigid walled line, and a 3-way tap. Alright, so now we've gone through what we're basically going to need and the indications. We'll go through some basic waveform interpretation. Alright, for waveform interpretation, I'll be pointing at a rough rendering with a pen. So here we have the x-axis. This shows pulse pressure. It'll show the blood pressures. It'll have a line for the mean arterial pressure. Y shows line there. So the first part here, we have the systolic upstroke. Now, the systolic upstroke is the ejection of blood, and it's a peak aortic flow. Now, it is thought that the angle of the slope here represents a contractility of the ventricles. Now, a steep slope is thought to represent a strong contractile force, but a more shallow, slack slope would represent a weak contractile force. Now, up here, we have the peak systolic pressure. This is the maximum pressure in the arteries. Next part, the systolic decline. Now, this is decline in the arterial pressure as a ventricular contraction comes to an end. Next part here, there. This is the dicrotic notch. This is thought to be a brief increase in pressure from the aorta when closing. A sharp, obvious notch represents normal closing of the aortic valve. A smaller absent notch will reflect some type of aortic deficits. But we've got to remember, the more distal from the heart, the less we'll be able to notice a dicrotic notch. Now, if it's in the dorsalis pedis or the posterior tibialis artery, we're probably not going to be seeing the notch there. Next part here, the diastolic runoff. This is a cessation of systole. It's after the aortic valve has closed. This slope represents the degree of resistance left over. Now, it's thought that a shallower slope represents increased resistance and vasoconstriction, where a steeper slope, where the pressure just disappears and goes down to the end diastolic pressure, this is thought to be less resistance, for example, through vasodilation. Now, the end diastolic pressure, which is the bottom here, this will be our diastolic pressure on our blood pressure. This is the pressure exerted back on the aortic valve. Less compliant arteries increase pressure, more compliant arteries will decrease the pressure. And that is basic interpretation of what should be a normal arterial waveform. Now we'll go through some not so normal waveforms. All right, here we have another dodgy rendering of an arterial waveform. We have some of the numbers here. We've got a heart rate of 50, not great, an average blood pressure, and an average mean arterial pressure. Now, as we were going before with what was normal, here is some that's not normal. We see the systolic upstroke here is quite slack. Now this is thought because the contractility of the heart is quite average. So we might be seeing things like this in an AMI where there is a big zone of ischemia, necrosis that is not contracting, or in a patient with a significant history of MIs, they've just got a very scar tissuey heart. We might be seeing something like this. All right, we'll go down to the next one here. More observations. Very, very average. As we can see here, same thing, a very, very slack systolic upstroke. So contractility of the heart is average, maybe because the preload is not quite there. The heart is not stretching out and contracting efficiently. The diastolic runoff is also near vertical. So this is because there is less resistance and vasodilation. So we might be seeing this in a septic patient or a patient with anaphylaxis, a distributive shock type of patient. Now, some basic principles of safe transport with the arterial line is if it does become dislodged at some time, which God, I hope it doesn't, direct pressure elevation, as this will be an arterial bleed, the cannula has been in an artery. Ensure that the line is not tangled, it is clear, non-obstructed, do not interfere with the circuit, just don't touch it unless you need to. If flushing is required, do not flush clots or bubbles into the patient. We've got to be sure to aspirate them out with a syringe, and we can use a 3-way tap to do that. Regularly check distal neurovascular observation, keep the limb with the arterial line in it visible at all times. Now, the more complicated principle of safe transport is based around maintaining the accuracy of the readings. The system should be checked and calibrated every time the patient is moved around just to ensure diagnostic accurate readings. We want to transport the patient between supine and 60 degrees semi-Fowlers to ensure accuracy. Now, calibration. This involves leveling and zeroing. This ensures consistent, accurate blood pressure monitoring. Now, leveling. Sorry, this is quite boring. I'm going to have to just talk through this because, like I said, I have nothing to demonstrate with. Leveling, we want the transducer leveled at the phlebostatic axis. This is a standard reference point on the patient for a baseline consistent transducer placement. This is in line with the atrium, which most accurately reflects central blood pressure. Now, we can find this at the fourth intercostal space, mid-axillary line, and that is a level where we'll keep the transducer. Secondly is zeroing. This ensures that the effects of atmospheric and hydrostatic pressure are eliminated on the transducer. The pressure of the fluids in the bag is all zero. Now, to do this, we're going to position the patient in the position that we want them. We're going to have the transducer at the right level. We're going to do the square flush test, which I'll go through after this. We're going to turn the 3-way tap on the transducer so it is off the patient. On the monitor that will be showing the waveform, we're going to press 0, and this will zero the unit. We'll ensure that a 0 appears on the screen. We'll replace the 3-way tap so it is open to the patient and to monitoring. All right, now we'll go through that funny sounding square wave test. All right, now the square wave test. Here are some more rough renderings of some variations of the square wave test. Now, this test is to test the dampening in the line. Dampening is the pressure exerted on the diaphragm of the pressure transducer. This test involves a rapid flush while monitoring the projected wave. This funny looking thing here. Projected wave to determine the accuracy of the pressure transducer. Now, if we were to do this, this is what we would see on an adequately dampened line. We would just see 2 oscillations only. 1, 2. Now, an over-dampened line, the over-dampened line, there is too much pressure on the transducer. And in doing this, we'll push the fluid, we'll see the square wave, there'll be 1 oscillation only, and then it'll go back to normal. Over-dampened line, we're probably not going to see the dichrotic notch. As you can see here, it's just a boring waveform there. The issue with an over-dampened line is it'll underestimate the systolic blood pressure, and the actual systolic should be here, and it'll overestimate the diastolic pressure, so you'll get inaccurate readings. Some causes for this, the pressure bag's pumped up way too high, the fluid is running too fast, there are air bubbles, clots, kinked or poorly placed arterial catheter, it's in the wall of the lumen or something like that. Now, an underdampened line, the other way, there is not enough pressure exerted on the diaphragm and it is too free to move. Now, this will show multiple oscillations. It'll keep going depending how underdampened this is. Now, underdampened line, it'll overestimate the systolic blood pressure. The actual systolic will be somewhere down here, and it'll underestimate the diastolic pressure. So again, you're not going to get a consistent, accurate reading. Some common causes for an undampened line is not enough pressure in the pressure bag, or there's no fluid at all, you haven't primed the line, excessive tube length, or there's a very high cardiac output. All right, now we'll go through some considerations. Now the considerations or transporting a patient with an arterial line is, if the pressure transducer is not leveled at the phlebostatic axis, there will be different pressures exerted on the diaphragm. For example, there'll be an increase in pressure when the waveform is below the phlebostatic axis, or there'll be a decrease when it is above, so this will not show accurate pressures. The displayed arterial waveform, or the mechanical systole, will not be in time with the QRS complex on an ECG, which is the electrical systole. The waveform will be slightly delayed after the QRS complex because the electrical systole will happen before the mechanical. The position of the arterial line will show changes in the dichrotic notch when moving further from the systolic peak, and will go, the further you go down the arterial tree, like down to the leg, if you go to the posterior tibialis artery, for example, the dichrotic notch will fade away into nearly nothing. There may be variations in readings when the patient is positioned lateral. This is due to difficulty in leveling the transducer. So it is very important that we try and keep the patient on their back between that 0 and 60 degrees. And if it's not been done already, the catheter will need to be sutured to prevent any dislodging during transport. Right, thanks for listening. That is arterial line waveform interpretation and safe transport. Bye-bye.